All right, one last thing on the review. I think I just had a typos pointed out to me. I think I have the answers in newtons, even though the forces are in pounds. So these should be pounds is what they ought to be. I think I screwed that up. So there we go. Pounds for these, okay? You would never want to convert. You know, if you're given something in pounds, just stay there. So that's just a error, okay? Should be pounds, all of them. All right. So we're good with that. Now we got some homework due Monday also, so we ought to go over that. So these are frame and machine problems. So let's have a look at these. So 321. Now these have some similarities to trusses in that you pull them apart into pieces, but you know they're more complicated than trusses because they're not all two-force members. Now you can have two-force members in frames and machines, but you can't assume that something is a two-force member. And well, I mean, they're not all two-force members. You can't assume if you can see something about them that indicates it's a two-force. So for instance, what you're looking for on a two-force member, this is 321, would be two pins with no applied forces in between. So it looks to me like CE is a two-force member. Okay. So when they're there, you want to be able to identify them. So CE is a two-force member on 321. So if it is, then what you want to do is to show it simply as a force. So what I'm doing there is I am showing CE going to the right. Let's see, that's CE going to the right on EF, okay? And then I show it coming back to the left on BCD, okay? So that's what I'm doing there. So I come up with an exploded view, which is always an important thing to do when you're coming up with these frame and machine analyses. You want to generate an exploded view of the object. So what you want to do first is define any two-force members and then draw up an exploded view of the object. The intent with the exploded view then is to show each part of the frame and machine as a free body diagram. It's important to remember to turn the forces around as you go from one connected member to the next. Okay. So what I'm going to want to do, I want to find the forces in the pin at B. So initially I'm going to look up here and I'm going to realize I have 4 unknowns, which is one too many to solve them all out with statics. However, I can take a moment about A and solve for BY. I'll notice that right off the bat. So I'll go ahead and do that because it's straightforward and easy to do. Okay. So when I look at that, I'll use that top free body diagram. And I think what I would do with that is I would sum moments about A and set that equal to 0. And what I would then have would be minus 7, which is the dimension, to BY. And then I would have plus 7 and 6 make 13 times 400 pounds. So 400 pounds times 13 inches. And that will allow me to solve for BY when I do that. And that's 743 pounds. So this will be 743 down. And that means this will be 743 up. And you do have to remember to turn them around as you go from one connected part to the next. Yeah, question there?
Is it still, is BY still at 7? Would you still consider it 7 inches since it's in the center? Or meters?
Well, it's dimensioned at 7. So I don't know quite what you mean.
Oh, sorry. I was looking at it. Well, I guess it's, yeah, okay.
So you're saying, like, if you were going to take the moment about D, you would probably use the dimensions on the bottom.
Yeah. I got
Oh,
it.
yeah,
Right.
yeah, you would.
Another,
We're good?
yeah,
Okay,
I got
good.
the 7.
Yeah, no worries, okay. All right, now that gets me by, but it doesn't get me bx, and I can't get bx by using abg. So I'm gonna have to come from the other side over here. And when I do that, I'm gonna go, okay, I need to kind of work my way through CE. That's how I'm gonna get to BCD. So what I can do, I can take moments about F. So notice I'm not solving everything out on these, I'm just solving what I need. Okay, and I've got that force to the right at 600 pounds. So what I'm going to have there is 600 times 3. That's clockwise, so that'll be negative 600 pounds times 3 inches. And then pulling back, I've got counterclockwise, I've got FCE times its moment arm, which is 3 and 3 makes 6 inches. So I'll get 6 FCE is going to be 1,800, I think, pound inches. So I can solve for FCE. And that is going to be 300, I think. Okay. Now what that's doing, it's pulling to the left on EF. So that means it's going to pull to the right on this one. So this will be 300 right there. So now what I can do with the last one is I can look at that and I go, I got one unknown on the top. It's BX. That's the one I want. I can take moments about D. So, you don't have to solve everything out. You just want to come up with a strategy to get to the one you want, okay? So I can take some moments about D and set that equal to 0 and run through the stuff on that to figure that one out. Okay, so what I would have there would be what? Negative 600 pounds times 3 inches. Negative because it's clockwise. And then I'll have plus 743 times a moment arm of 4 inches from down below. And then I'll have that BX. As I have it drawn, it's a negative. 6 and 4 makes 10, so negative 10 FBX. So 600 is, oh, I screwed up. That's 300, isn't it? Let's get a check on that. And I think I switched the dimensions around. It's 300 times 6. It's not 600 times 3. Yeah, okay, so let's get that cleaned up. Thank you.
It's just that they look very similar. They're both like 94R things.
There we go. We good? I think we're good now, right? Same number, but yeah, I switched them. So 300 times 6. Okay, there we go. Okay, and you can solve for FBX. And that'll get you the one that you want, and that's 117. Okay. So there's a fair example of a frame and machine problem. Okay. So you kind of work between the different members to solve out what you want to know. You got to remember to turn them around, turn the forces around as you work from one member to the next. And also, it's handy to identify any two force members that might be acting on the object. Okay. So we good with that? Okay. Okay, there's the next one. Okay, see any two force members on that one? I think so, yeah, two force member there. This is kind of similar to the other one, except that you have this pulley thing going on. So yeah, this is a little goofy, this one. All right, so I'll put the 48 pounds. Remember, you can move those cable forces right to the pin. So to avoid any sort of odd dimensioning things you might need to do to get to the tangency points on where those cables come off the pulley, the typical thing to do is to move both forces onto the pin. so I got those moved over there. So now I can go ahead and pull it into pieces. What I want to do there is find the force at D. So I'm going to have to work my way in from both sides to get that, very likely. Okay, so I'll start over there on the right, because what's going on at D, it looks to be a little bit more than I can handle just by looking at that bit there with CD. CDB, okay? So I'm going to start at the right-hand side, and I'm going to get FEH here first, using that vertical member there, and that is 45 pounds. Okay, now once I've got that, I can transfer it over to the vertical DF there, and I can find DX there on that one, and that's 20 pounds. And once I know what DX is, which is this one, remember to turn it around when you put it on that BCD. I can solve for FDY then. Okay, so that's how I would work through this one. That's the sequence, and that'll be 51.6. Okay. Yeah, those are all moments. Taking about the bases usually. And again, don't hang up on solving out each member completely. Just get to what you need. If all you need there is dx and dy, just do moments and kind of skip your way through and get over there and do it. All right, so are we good with that? We got any questions on that one? All right, now those are both frames. The first one there, the first one had just links in it, sort of, or just simple pieces in it. This next one had a pulley. So you do have that deal where you take the forces from the pulley and put them right at the pin, like so. Okay. All right, the next one is a pair of vice grips. I've got a simplified version of that right there. So you're going to take that and pull it apart into its pieces. So we got the upper jaw. The lower jaw has both a handle and a lower jaw itself. And then do you see any two force members on that? Yeah, that's the lock. Yeah, that's the locking arm is what that is, and that's a two force member on purpose. They make that to be that, because what it does, it locks that lower jaw in. So that's a two force member there, and we got a D and an E down here.
So two force members, anything that connects two members?
Yeah, it has two pins. It's a linkage with two pins and no forces in between. So then it can only have forces at the pins, and that makes it a two-force member. And if it's a two-force member, it's either in tension or compression. You know the direction of the force once you know if something's a two-force member. Okay. Good with that? Okay. All right, so that's our diagram there. Now what we're going to do is kind of work our way over. Now that two-force member there, I've got shown. I'm going to start now. That upper handle there might be a little bit more than I can start with. So I'll probably start with the lower handle because it's only got those two pins and one of them is a two force. So I'm only going to have three unknowns on that lower handle. Probably start there. That would be the place to start. And then once you do that, you can probably solve for FEC, I think it is. Okay. And you can get that, and that's 754 newtons. Okay. Like so. And then once you've got that, you can go to that upper handle, and you could solve for the clamping force. So it's pretty quick on this. You just have to be able to see, where your opportunities are to solve for things, and that would be 642 newtons there.
DY equal to BY?
Is dy equal to by?
Yeah, are they also a 2/4 member?
What?
C, B to D?
B to D?
Yeah.
B to D.
I mean, it's not a straight
Oh, but the
bar.
jaw, there's the force in the jaw though.
3/4 member?
Yeah, 3/4. So that 3/4 you can't do anything with really.
So but would the force, like, once you solve for dy, could I assume that was equal to dy?
No, because you got that clamping, you got the force in the pipe, so I don't think you can do much with that. You could solve it out with equations, but I don't think you can assume much about it that'll help you. Okay, so I would get that 2/4 member using the lower handle, D there, and E, and then once you've got the 2/4, go up to the upper one, and you can solve for the jaw force. Okay. You okay with that? All right, this one's a little bit involved, 325, but it's the same strategy. Now, you got a bunch of pulleys going on there, so you want to, kind of figure that out. Now, what you've got here is, this is 1200 newtons, so I'd start with that. Why don't we jump ahead here to this one here? Or actually, no, let's not. Let's just stay here. All right, so this is 1200. So if that's 1200, what are the forces in those cables? If I've got 1200 doing this, and I got those cables. Now let's kind of do a little check here. That's one cable, isn't it? It is, okay. So that means the force is equal in it everywhere, okay? In statics, the force in a cable is everywhere equal. So those are both 600, right? You all good there with that? Okay. Now I know that those are both 600. So what I've got is, this is 600, and that's 600. Now this will be 600 also, as will that. We got a bunch of 600s here, as will that, okay? So there's all my 600s, because I know what the force is in that cable. Now, what I can do, for simplicity, is take the two 600s from the pulley at E and move them to the pin. But they both have to go. If you move one, you got to move the other. So I'm going to move this one over here, and I'm going to move that one over there. So I'm going to do this, 600, and then 600. And when I do that, that goes away. You okay with that? What did I just do? It's magic.
So we just get rid of all the weights and the G and the whole thing just goes?
Yeah.
So easy.
Everything goes to 0. I had a fluid mechanics teacher like that. He'd just scare everybody with these partial differential equations, and then he'd make everything go to 0, and everything was okay. So, all right, now I've got this one and that one. They're both pulling on the large pulley, correct? So what I can do is I can transfer them to the pin at E if I want. So I can put them both at the pin at E. They're both 600. And when I move them, then those are gone, because I can move them both at once to the pin.
Isn't the one already at the pin at E?
There is one at the pin, but I'm moving the other two. So the net downward force in the pin will be the 600 that was there originally, plus the one I moved. It's going to be two 600s. It's going to be 1200. But when I do that, I also have to move the one horizontal down to the pin.
What about the other side?
The other side, I'll put them both at the pin at C. 600 and 600. So I'd probably do that before I got too deeply into it, okay? That'll make my free body diagrams a little simpler. Yeah, question there?
I just don't understand how you're allowed to do that. Like, how you can just move it over right there.
It's the laws of physics. I don't know. What the deal is we went through this a little bit at the beginning. What's going on is there's no moment about the pulley. The thing's in equilibrium. So you've got 600 here and 600 there. Now what you've got then is the reactions of the pin on the pulley are like that. There's no net moment. So right at the pin, you've got those two reactions. That's the pin on the pulley. Now what the pin will then do to the armature is in the opposite direction. So when you get to what happens to the armature, it looks like that, 600 and 600. Yeah, right, which just simplifies it.
Okay.
And that's the logic chain, but you don't need to, once you got that, you can just put them at the pin, you're good. But you got to move them both at once. You can't just move one to the pin and not the other. Yeah.
When you have it on pin C, does that not just translate to pin D as well, or it's not that simple?
No, it's not that
Okay.
simple, yeah. Okay, so, all right, so given that, I get to this free body diagram here. So I've got that top horizontal, I've got BX, BY, DX, DY, and I've got two 600s down at the far end and one 600 to the left. So there's my free body diagram of the top one. All right. And then I've got the angled one where I've got AX, AY, 600 newtons at C, I think that is. Yeah, it's C. And then I've got the DX and DY. So what I've got here, see, I got too many unknowns. I've got BX, BY, DX, and DY on the horizontal one, and I've got AX, AY, and DX and DY on the angled one. So I'm going to have to work them against each other because they have the D forces in common. So what I would do here, I'd probably go with a moment about B. Set that equal to 0 and do that stuff, and I can find dy. It's 2133, and that's newtons. And then once I've got that, I got to turn it around and I put it right there. See, I found dy using the horizontal one. I could get away with that because if I take a moment about B, I've got 1, 2, 3 unknowns intersect there. I can solve for dy. Okay. Now, I can't do much more with that horizontal one, but what I want are the forces at D. So I can turn the 2133 around, put it on the angled one, and now what can I do? I can do a moment about A, right? And I can solve for dx. And that comes out to be 3009. Okay. So I had to break that force down a little bit and put those cable forces at the pins first to get those free body diagrams. That's a key step in doing this. And then once I have them, I kind of again have to employ some strategy. I've got 4 unknowns on both of those things. So I had to work with the horizontal one first and kind of get that one I could get, dy, which turned out to be one I wanted. And then I can turn that around and put it on the angled one and solve for dx. That's the strategy on that. Okay. Questions on that? You doing all right? Okay. All right. Okay, the last one is this. I'm just going to let you figure this one out. The math on it's quite simple. You just got to find the force in the cable. It's how many cables do we got? Do we got one? Yeah, and I just draw a picture if I want to know. I do that because I've seen them in some books where they got 3 or 4 cables, but that's only one. Figure out what that force would be. Okay, and I'll let you do that one. Okay. Are we doing all right with that? So I'll see y'all Friday. Remember to bring a calculator, non-programmable calculator. I'll have some with me. Okay.